Okay, so let's go ahead and get started. So let's talk a little bit about your lab, which is also kind of a prep for your exam. So you guys recognize that delta H is like a form of energy, but in terms of energy per mole, it's enthalpy, right? You guys remember that from thermo?
Yeah.
When we talked about thermo, right? And so that's going to be kind of valuable and important for what we're doing. So if you're getting a certain amount of energy and you kind of want to accommodate that, right? We could sit there and kind of set that energy sort of equal to each other, unless there's energy that's work involved in it as well. So we can kind of say like our delta H and our delta E, sorry, moles, delta H times delta E plus the energy associated with work is going to be comparable to each other, right? And so actually it should be okay. And so since we can sit there and make that assumptions, and if we make an assumption that there's no work being done on the system, we can just kind of set these guys equal to each other. Does that make sense?
Yeah.
Okay. And so you're going to be using that concept, and then we know that we can calculate the change in energy in terms of the H nu. But in this case, we'd also want to take in consideration the number of photons that we're also accounting for. So like the moles of photons. Make sense?
Mm-hmm.
Okay. Okay, so I just wanted to say that so you guys had a kind of an understanding about it, right?
Yeah. So is that the unit right there? Is that an N?
Yeah, and for
Okay.
number of moles. Yeah. That's our standard unit for number of moles. Okay. The other thing that I wanted to talk about that I kind of realized I didn't talk about, and you actually brought it up, Selena, if you recall. We were talking about paramagnetic and diamagnetic. So when we're talking about let's say we're in a 3p orbital. Okay, so paramagnetic is basically when you have electrons that are unpaired, right? So this would be an example of paramagnetic, and this guy would be an example of diamagnetic, because these two electrons are unpaired, not under those circumstances. Does that make sense?
Yeah.
Okay.
So, I watched a video on this kind of thing. So if you have like unpaired electrons for like an element, it's magnetic, right?
That's right.
If you put a magnet up to it.
That's right. And so you can kind of hold that electron or that atom into space in suspension by just having those magnets available.
Mm-hmm.
Where if it's diamagnetic, it'll flow right through. Does it make sense?
Yeah.
And that's again because these guys are kind of canceling each other's out with the opposite spin, where these guys aren't going to be able to cancel each other out. Okay. Okay, good. Hey, Cassie, how are you?
Good. Sorry, I had to drop the rug right off at daycare.
No, it's okay. It's okay. Believe me, I know about having a life. You know, it's not planned. Okay. So we're almost done with this whole bonding aspect of things. We have a couple more things to go over. We have chapter 8. We're going to kind of whip through chapter 8. There are going to be parts of it that I'm going to hold you responsible for. And parts of it, we're just going to have to, you'll pick up along the way. So ultimately, okay. And we also need to finish up chapter 7. There's the major part of chapter 7 that we need to finish up is molecular geometry. Most of you guys have kind of had it. Kayla, I don't know if you have, because I don't know if you took 1A, I mean 2A, 2B, 2A, or you just went straight into 1A.
Yeah, I don't think I.
Okay, so if you have any questions on it, if I'm going too fast, let me know, and I will slow down, but I need to kind of pick up the pace so that I can try to shove as much stuff in your guys' brain as possible.
The worst part you want to go quickly on.
It's not that bad, really.
Oh, I hated this part, Dr. Henry.
It's actually a lot of fun when you sit there and you're looking at it and you're like, oh, okay, I get it. So,
yeah, it's like the trigeminal with the yeah. I was like, what? All right, I'll try to.
Okay, so I'm gonna try to give you guys a couple more problems. Can you guys see my screen?
Yeah.
Yeah, I'm gonna give you guys a couple of problems with this because the reason why I want to give you guys problems of this sort is because in reality, you will have to use this more so than, let's say, the molecular geometry comes important if you're looking into structures. If you're planning to go into structure dynamics, like say protein structures or anything like that, that's going to come important in that regard. And it also kind of gives us an idea of where things are going to attack. It's going to be important for organic chemistry. So if you understand the angles and stuff like that, and then which angles would be more susceptible for like exchange of elements and stuff like that, it kind of helps. Okay. But you can kind of live without it, but it is something that you're going to end up having to pick up again in OChem. So, sorry, Cassie, can't get rid of it. So we're going to be talking about molecular structure and polarity. Okay, so we're going to focus a lot on the VSEPR theory, which is the valence shell electron pair, repulsion theory, and we're also going to talk about bond polarity versus molecular polarity, because there's a distinction between the two. Okay. So when we talk about certain things that you want to keep in mind, we're going to give you certain definitions. So we have what we call the bond angle. Bond angle is the angle between an atom that is covalently bonded, So like hydrogen and carbon versus carbon and oxygen. So we would be looking at the angles between these two covalent bonds, okay? So that represents our bond angle, and we know that bond length is just basically the distance from this carbon to this oxygen, right? So. Now, you also want to kind of pay attention to units. We know that the bond angles are going to be pretty small. So we're talking about angstroms. we're talking about picometers, right? If you get stuff like millimeters and stuff like that, you know there's probably something wrong with your calculations. So you want to kind of use that as guides to sit there and when you're doing that math to make sure that you're right in the right ballpark. Okay. Okay, so so right now this is an example of a molecule. So these guys have 3 different attachments, right? 3 attachments that are to it. So we have a carbon that's attached to one of the hydrogens, a carbon that's attached to another hydrogen, and a carbon attached to an oxygen. Now, in theory, we know that if we drew the Lewis dot structure on this, this guy would have these electron pairs that are sitting out, right? Those electron pairs are going to affect how this molecule or this molecular geometry, right? And so the effect that it has is going to be minimal overall, but it's still going to have an effect. So, but these guys, they have 3 attachments. So you have a center and you have 3 attachments. If we think about that, have you guys played with, what is it called? A widget spinner? Those widget spinners?
Yes.
I know what you're talking about, but I never like messed with them though.
I should actually start putting those in kits because they're kind of fun. And you learn stuff from it, right? So in the case of a widget spinner, a lot of them are 3-pronged, right? And if you think about it, we're talking about a circle. Do you guys know the angle of a circle? We use this term quite a bit, Reg 360, because it's completion, right? It's completing that circle. Anybody know the angle that's associated with a circle?
Negative.
Not the charge, not the charge that's associated with it.
Negative as in 9 German for no.
Okay, no. Okay, so if we think about it, a circle is 360 degrees total. So from 0 to coming all the way back around, if we do this whole thing from this point to this point, it's 360. You guys remember that from geometry?
Never took it, but
Never
I know
took it?
that.
I didn't
I
pay
know that
attention in
it's
high school.
Okay, so altogether, if you go from 0 to 360, it's 360 degrees.
Yep.
Okay, so it's 360 degree, it would be the angle. So if we break up 360 degree into 3 parts, what would be the angle of each part? So we're saying equal parts, 360 degrees. What would be the angle from here to here, here to here, and here to here?
120?
That's right. So that would be 120, 120, 120, 120. Okay, make sense? Okay,
Yeah.
so if I broke it up into 4 parts, what would be the angle?
90.
Yeah. So in that case, it would be 90, right? Okay. So if I break it up in half, what's going to be the angle? From here to here.
180.
Okay. Piece of cake so far?
Yeah.
Okay, good. Okay, so knowing those degrees are going to be important, but we're also talking in this situation, we're really talking about something that is planar. You guys know what I mean by planar. Planar means like a flat sheet of piece of paper, right? It's flat, right? It has no 3-dimensional structure associated. Where when we're talking about a lot of molecules, some of them will be in a planar situation, and they kind of let us know, right? And then some of them will be in a 3-dimensional situation, right? And so in that context, toys. Of course, when I'm looking for my stuff, it's never here. So we'll do it like this. We'll do old school, right? I do have it. I know where it's at. Okay, so here we have a balloon. And the center represents the center atom. Each of these represents an individual atom, right? So in theory, that's kind of close, isn't it? Yeah, there you go. In theory, this guy, each of these angles between here is what?
120.
120. So if I add a fourth one, and it's no longer planar, it's actually three-dimensional. This guy is called tetrahedral, right? Because in theory, all of these angles are exactly the same. They're all 109.5 degrees. Okay, because we're talking about a three-dimensional structure in this case. Does that make sense? So when it's planar, and we have a center atom and three attachments, that guy, this guy is called, it's called Trigonal Planar. Okay, so what we have here, three attachments, Trigonal Planar. Okay, if I have two things attached to the center atom, what is this guy going to be called?
Linear?
Linear. Okay, and I'll show you an example of that here in a second. Okay, so the thing that I want to point out here, because of these electrons are pushing these guys a little bit further. So the angle is a little slightly off from 120, right? So this will be like 121, and this guy will be 121. And then this guy will be 118, okay? So because we have these electrons here, they're gonna cause repulsion, right? They're gonna push the other guys a little bit closer together. Does that make sense? Yeah, no, maybe?
So the more you get, the closer they're going to push towards each other?
Yeah, so if you have
Okay.
more, so if you have more lone pairs, it's gonna affect the guys around it, in other words. Does that make
Okay.
sense?
Yeah.
So if we had no lone pairs, it would be exactly at 120. If we had no lone pairs on oxygen here, it would be exactly at 120. Okay, but you're just gonna slightly change the angle. You're not gonna change it by a lot, just by a little bit. Does that make, are we clear? Okay, so here's an example where we have those two attachments. Okay, so we have fluorine here, and beryllium only likes to be attached to two things that have 4 electrons around it. The angle is 180. Now, the reason why it's 180 is because we have fluorine here and we have fluorine here, right? They're equally, they have the same number of valence electrons, so they're both pushing equally against each other. So that's going to be exactly at 180. Okay? Good so far?
Yeah.
Yep.
Now remember, there's only 3 of you guys, so you guys have to answer. You can't just sit back and watch. Sorry about the text, it's not the prettiest, but the pictures are beautiful, and then we'll talk through it. Okay, so here we have, this is basically showing you the spatial arrangements with balloons, in other words. So here we have a center atom, and then we have one attached to one and attached to another. Okay, so then in that case, we're going to have 180 degrees angle between the two, right? This guy is going to be called linear, right? And so we have what we call the electron pair geometry and what we call the molecular geometry, okay? It just so happens that the electron pair geometry and the molecular geometry are going to be exactly the same in this circumstances, right? Because in this case, we have H, the E, H, so you have 2 attachments, right, to the beryllium, okay? So in that case, it's going to be linear. The angle is also going to be 180, okay, on both sides. Here, where we have boron attached to 3 hydrogens, the angle is going to be 120. So this guy is going to be trigonal planar. Let me type that out so you guys can see it clearer. Okay. In the case of 4 attachments, carbon with 4 hydrogens attached to it, so then that guy is going to be tetrahedron. And all of the angles are going to be 109. And then in the case of where we have 5 attachments, so in one case, we're going to have 3. Oh, let's use their little balloon structure. We'll have 3 in one plane, and then you have 1 at the top and 1 at the bottom. So then that's giving everybody the furthest distance they can give them without anybody, being too crowded with each other. Okay, so the up and down one here is going to be 90, but in the planar region, it's going to be 120. So this guy, because that 120 part of it is going to be called Trigonal Bipyramidal, because technically you have 5 attachments. So you're forming a pyramid. And then, so there's a pyramid, top and bottom. Okay, so that's the reason why it's tri meaning 3, gonal, bipyramidal, 2 pyramids. Make sense? Cassie, you have that look.
Get there.
Sorry, my R sticks a little bit. Okay, so it's not the prettiest picture, but so in other words, you're going to have 3 sides, top and bottom. Okay, this here will be one side, this here would be another side, and then on the back side we'd have another one. You see it? So it'll look like this. Sorry, I'm not an artist. If you haven't figured that part out yet, maybe I should draw it like this. There we go. Okay, so then the last one, when you have four things in the same plane, each of these angles are going to be 90 degrees, 90 degrees, 90 degrees, 90 degrees, because there are four things in that plane. And then you're also going to have 90 degrees going top and bottom, right? So in other words, they're all going to be 90 degrees from each other. Does it make sense?
Mm-hmm.
Okay, so 90 degrees here, 90 degrees here, 90 degrees here. Okay, so everything's going to be 90 degrees. And then this guy is going to be octahedral because it has 8 sides, right? So if you look at it, kind of, so we have a side here, we have a side here, we have a side here, and then we have a side on the back side, top and bottom. Okay, makes sense? Selena?
Yeah, this is kind of like a refresher from like the summer.
Yeah.
Yeah. It's been a while.
Yep, brushing off those cobwebs, right?
Yeah.
Okay.
Dr. Henry,
Yeah.
is it like a bent structure too? Because I
Yes.
remember from 2A, like the structures that look linear, but the lone pairs are what push it to look.
Exactly. We're going to get to that. So right now we're talking about things that have complete attachments, right? So these are going to be the, again, this should be molecular geometry because we're talking about them being attached to atoms.
Okay.
And we'll talk about lone pair geometry because that's going to be a little bit different, plays a different role. Things are going to look similar, right? In terms of they're going to be absolute what they are in terms of the electron pair geometry, but what the actual structure going to what the actual structure looks like is going to be different, or the molecular geometry can be different. So the molecular geometry change, but the electron pair geometry is going to be exactly the same depending on the number of attachments. So those attachments can be electron pairs, or they can be atoms. So just in this case, all of this right now, because we're talking about things that are physically attached, these guys are all like attached to other atoms. These guys would all be molecular geometry, okay? But when we're talking about electron pair geometry, these are also considered to be the electron pair geometry as well, okay? Now the electron pair geometry are only going to be this, it's going to be linear, trigonal planar. We also have tetrahedral, trigonal bipyramidal, and then octahedral, okay? So those are the things that they can be, right? And that's just taking into consideration both attachments to atoms and attachments to lone pairs, okay? So, and we're going to talk about that here in a second. I know it's not making too much sense right now, but once we start talking about it, it'll be a little bit clearer. Okay, so this guy is an example of tetrahedron, right? So you can see the carbon is in the middle, and you have 4 attachments on the outside. They're all going to be at what angle to each other?
You said 109.5?
109.5, exactly. Okay, so here we have ammonia. Ammonia it has a lone pair. Here's nitrogen, and it has 3 hydrogens. So if we talk about the electron pair geometry, because it has 4 things attached to it, it has the lone pair, 1, it has 3 hydrogens, total of 4, it's going to be tetrahedral. Okay. Good, bad, or ugly?
Dr. Henry?
Yep.
Wasn't there like an equation to figure out the electron pair geometry? I forgot what it was. It was like with bonds in the lone pairs or something.
Yeah, so it's just going to be the sum of both, right? So there's not an equation, but there's a nice little table. What you're talking about is you're talking about when you're bonding two things, whether they're really going to bond or they're not going to form a bond and stuff like that. That's called bond order. We talked a little bit about that.
Okay.
Okay. So
Yep.
This guy here, right? Because the lone pair, when we're talking about the lone pair, we don't see the lone pair when we're talking about the molecule itself. The lone pairs are kind of invisible to us. So what we see is that the angles are shifted, right? So normally it would be 109 if it was truly tetrahedral. Each one of these should be 109, right? 109.5, each of the angles. But because these electron pairs have such a repulsive effect, they're going to change that angle. So that causes the angle coming down here to be different, right? So this guy's going to be pushing a little bit harder. So the angle between these guys are now going to be here are going to be 106. 106.8 or less than 10. It's hard to see. Or it's just going to be slightly less than 109, right? So the lone pairs are going to affect how they react. And then this guy is going to look different. So this guy here is now called the molecular geometry. It's called Trigonal Pyramidal. Okay, because it's a three-sided pyramid. Okay, three, pyramidal. Okay, and so, but this is what it's really going to look like. Okay, so those lone pairs shift the angle, so because they're going to cause more repulsion. They're going to shift the angle slightly. Does that make sense?
Yeah.
Okay, so this is a nice little table with all the names. Again, I apologize. I couldn't get for some reason, it doesn't looks great on the screen, but when you import it into the slides, it looks like crap. So if we have two attachments to a center atom, they could be lone pair, or they could be a true attachment, right? So in this case, these guys are going to be true attachments. There are no lone pairs involved. Here, this is assuming there's one lone pair. This is assuming there's two lone pair. This is assuming there's three lone pair. This is assuming there's four lone pair. So here we are going to have two things that are going to be attached to our center atom. So this guy is going to be linear. Simple, right? Here, if we have three attachments, right, three atoms attached to it, it's going to be trigonal planar. If we have two attachments and one lone pair, it's going to be bent or angular. Is this not looking familiar, Selena?
Yeah. I have a question, Dr. Henry. So
Yep.
like on the lab for molecular geometry, there's like some that have one attachment, like HF. And
And I'm like, well, there can't be a center atom that you can like pinpoint.
Yeah, but what would it be? I mean, you have H, this would be H, and this will be F, just to connect it together, right?
Right.
So what is that going to be?
Would that just be linear?
It would just be linear, right?
Okay.
Yeah, it's kind of like a sticks, you know, you're putting two things at the ends of a stick, and then it's just linear. Okay, so if we have 4 attachments, 1, 2, 3, 4, so we have 4 atoms attached to a center atom, so this guy is now tetrahedral. If we have 3 attachments and 1 lone pair, this guy's trigonal pyramidal, so that's kind of like our ammonia. And then if we have 2 attachments and 2 lone pair, kind of like water, that guy is going to be bent, or what we call angular. And that's why that's the reason why we draw water like a bunny ears, you know, or Mickey Mouse ears. Make sense?
Dr. Henry, remind me the dashed line, that one goes behind and then the solid is coming at you.
That's correct.
Okay.
Okay. So, and we know that the angle between the 2 attachments are going to be less than 109, right? Because if there's 4 things attached, all the angles are 109. So then these guys are going to be a little more than, let's say, just 1 lone pair. So the more lone pairs we are, the more lone pairs we have, the more it adjusts the angle that we're at. Okay? Does that make sense? Okay. So, sorry. So if we have 5, okay, 5 attachments, trigonal bipyramidal. If we have 1 lone pair, we have what we call a sawhorse. And I actually have to look up a sawhorse. I didn't know what a sawhorse was. Or a seesaw. Or a seesaw is kind of like this, right? Okay. And if we have 2 lone pairs, we have a T shape, right? The thing is that this guy is going to be a little less than 190. So it's going to be a little altered T. So it's going to be, it's like a little, kind of like a TP. So rather than a straight T, it's going to be a little altered. So it's going to be like that. Okay. And then if we have 3 lone pair, it actually is going to be linear. Right? Because then it's just these 2 guys are going to be as far away apart as they can be. And then these guys are just going to kind of, because they're equal lone pairs on each side, they're going to form a 120 perfectly. So all you're going to see is a linear structure in that situation. Okay. So in our last case, so if we don't have any lone pair, it's octahedral. If we have 1 lone pair, it's called square pyramidal, because now you're forming like a square, but it's a pyramid square. If it's 2 lone pair, we don't see the top and the bottom, so then we just basically form a square planar. So it's square in 1 plane, so it's square planar. And then if we have 3 lone pair, we have what we call the T shape. And then if we have 4 lone pair, then we have, again, a linear. Okay? Yeah, that look.
How can it be a square and a pyramid?
You could have a 4-sided square, right? Well, it's a square because it's your square components are, your pyramid is put on a corner. So I don't have a nice square block. Let me find a. So if we had a square, like when you're looking for stuff, you can never find it. I need to start bringing all my little shapes. So if we have a square and we put it on its side, this is a rectangle, but let's say it was a square. We put it on its side, it could form a pyramid, right? So you'd have two pyramids that are basically forming.
Oh, okay.
Yeah, on top and bottom. So, but it would just be a four-sided pyramid. Oh. Okay, so here's an example of trigonal bipyramidal. We have a top. We have 3 points and a bottom, right? So in this case, if we were talking about CL F4, CL F3. So its electron configuration, or I should say, its electron pair geometry would be trigonal bipyramidal, right? So you'd have those two guys, and then you'd have your fluorine. They actually put their fluorines here. Fluorine, fluorine, and fluorine. And then you'd have your two lone pair here and your two lone pair here. Okay. Questions, concerns, Cash? And so this would be the electron pair geometry. And then what would be the molecular geometry? You have technically have 5 attachments, 2 of them are lone pairs.
Would it be the same?
Nope. Let's go back.
Well, because octa is 8.
So think about it. It has 5 attachments altogether. You have 3 that are real attachments and 2 of them are lone pair. So 5 attachments and 2 of them are lone pair.
Oh, I was looking on the other one. Dang it.
Okay, so the electron pair geometry would be trigonal bipyramidal, but the molecular geometry is going to be T-shaped. Do you see the distinction between the two? So when you're looking at the molecular geometry is what you're going to visually see if you like crystallize the structure. You're not going to be able to see the electrons, right? Electrons that are lone pairs. Okay, so then all you're going to get is like a T-shaped structure. You're just going to get something that looks like this, right? And then, so you're not going to see the lone pairs that are sitting out here and pushing everything the way it pushes it. Does that make sense?
Yeah.
Okay. But if we're talking about the electron pairs, you want to take electron pairs and the attachment together. So then that guy would be trigonal bipyramidal. Okay. So what would be the angles?
Well, the one is 90.
Or a little less than 90. That's right.
Yeah.
One is going to be a little less than 90, and then the other one is going to be a little less than 120. Right. Good job. Okay. So determine the I gave you the first one. Determine the correct Lewis dot structure. The dash wedge model can predict the electron geometry and the molecular geometry for CO2, BCl3, and NH4 plus. Okay, so I did the first one for you. I did the Lewis dot structure. So what would be the dash wedge? So let me tell you what the dash wedge model was. So let's say we're talking about CH4. To help us to kind of visualize the structure, what we do is we make wedges. Wedge means it's, as Cassie was saying, it's coming out towards you. So it's like coming out at me. Lines means that it's either right above you or right next to you. And then the cell phone symbol or the dash means it's behind you. So it gives it that three-dimensional look to it. Okay. Are you there?
Yeah. So with this one, it wouldn't have anything, right?
That's right. So we would just draw it the normal way that we draw it because it's going to be linear, right? It's going to be
linear.
Then you're going to have your, technically your O's going this way, right? And then we predict it to be linear because they're going to be even on both sides. So it's going to be linear for both electron pair. So we're going to say EP for electron pair. And then for molecular geometry, APG. It's also going to be linear. For this guy that I just drew, this guy is going to be what?
Yeah.
So what would be its EP?
Is it tetrahedral?
That's right, tetrahedral.
Yeah.
And then it's MP. I'm sorry, MG.
Well, there wouldn't be any lone pairs, right?
That's
Because it's already got its full octet, so it'd be the same
It would be exactly the same. That is correct.
because there's
That's-
no. Okay.
So it'd also be tetrahedral.
All right, now I'm getting it.
Okay.
Yeah.
So what is BCl gonna look like? Let's draw the Lewis structure for BCl.
So B is in the center.
Okay.
3. There's 3. 2, 4, 6.
So you said 3 CLs.
Yeah.
Okay. Anything else? Am I missing anything, or is it good to go?
2, 4, 6, 8. Well, but there's only 6 around boron.
But what do we know about boron?
It was the exception?
It was an exception. That's
Okay,
right.
there you go.
So it only likes that 600.
So then
That-
it's
Yep.
So that's fine.
Okay. So then the wedge dash.
Um, would 1 CL be coming towards no, behind us?
Nope. Think about it. What is going to be the structure?
I don't know.
Is it gonna be like a flat structure?
It's going to be flat, right? It's going to be like a piece of paper. So you draw it flat, right? So you don't have to draw it 3-dimensional like one is coming towards you, because it's all going to be flat. It's going to be planar. So it's going to look like this. Okay. So then what is the EP, the electron pair geometry? EPG, sorry.
So that would be the trigeminal planar? 'Cause there's-
Trigonal, yeah,
whatever.
trigonal planar.
I can't see it. It's all smushed together. Sorry.
I know. Planar. Okay. And then what about the molecular geometry?
So is that the dashed one?
What do you mean by is that the dashed one? How many attachments do we have?
3.
Okay, we have 3 attachments. Do we have any lone pair on that center atom?
No.
Okay. And then we have 3 attachments that are going to be exactly the same. So what is going to be the structure?
Well, it's the same then?
It's going to be exactly the same. That's right.
So confusing.
Okay. So if you're not changing the number of attachments in any way, right? You have exactly the same number of attachments and they're real atoms. So it's going to be that same structure. Right?
So where can we do an example where it would be different?
Yeah, we can. If we had this, let's say we had, let's go. Okay, if we had BCl2 minus. So in other words, we're getting rid of
One of the. But now you have 1 extra electron, right, on top?
that's right. So we'll have a lone pair up top.
So is that where it's going to be the trigonal planar, and then it would be
That's right.
bent?
Yeah. So in that case, then the structure is going to be looking something like this. And then it's going to be trigonal planar and bent. That's right.
Bent. Okay.
Okay. Makes sense?
Quick question, Dr. Henry. Why would it be bent?
Because the electrons, these free electrons, they push down because they want to try to push things as far away from them as possible. that you have these lone pair electrons, they're going to be pushing down on the ones that are forming real attachments. So they're going to push down on these guys to make the structure a bent structure. Right?
Oh, okay.
Okay. So when we look at it all together, it's kind of like they have 3 attachments, but we really don't see that electron. So molecular geometry, all you see is what's really attached. And for the electron pair geometry, you see everything, right? So we have 3 attachments. We have 1, 2, 3 attached, really, but we only see the 2 things that are attached, and it's just pushing it down a little bit further, make it bent. Does that make sense?
Yeah, that makes more sense.
Okay, so I'm going to clear. And then what about this last guy?
Nitrogen's in the center. There's 4 hydrogens. But you lost an electron.
Okay. So what would be the wedge dash model? Selena?
Yep.
Wedge dash model?
Would it just be, would you have to do the wedge dash model, or?
Yes, you would in this case, right? Because it is a 3-dimensional.
Okay. So at least, so you'd at least have one, what's it called? The Wi-Fi looking,
Okay.
and then you'd have the other solid triangle, so you can tell which one goes in front and which one's behind the structure.
Okay.
So pretty much if there are more than 4 attachments, you would have to do the wedge dash, because 3 or less, they're
Yeah. If you have
on the
4,
single.
if you have 4
Okay.
attachments or more, yeah, you're gonna have to do the.
Okay, because I went back to the, was it 7.16 slide?
Uh-huh.
Okay, so that makes a little bit more sense.
Okay. And then so our molecular geometry,
So
our
that
MG.
one,
What was it?
there's no lone pairs. Tetrahedral?
Tetrahedral. Okay.
Yes.
And then our EPG.
Would that just be
Let's just
tetrahedral
say,
too?
That is correct.
because there's no, yeah. Good job, Selena.
Thank you, Cassie.
Got this.
Good job, guys.
For now.
Okay. So shall we make it a little more challenging?
Oh, here we go. Okay.
I am going to cry.
Wait, Dr. Henry, I have a quick question.
Yep.
So, for EPG, would you just count the bonds to figure out the structure? So like, let's say there's 3 bonds connecting, you would tell that it's trigonal planar, for instance.
Yep. If you
And
have,
then,
if you have 4 attachments, right?
yeah.
So anytime you have 4 attachments, any type of attachments. For EPG, it's any type of attachments. It could be lone pairs or it could be atoms, right? For
Okay.
molecular geometry, that's going to take into consideration only what you visually see, and then the electrons technically alter the shape. Does that make sense?
Those, the lone pair electrons alter.
That's right.
Okay.
Yep. Yeah. For the EP, it's always just the number of attachments that you have. You lone pair or atoms. It doesn't matter, right? And then for the molecular geometry, it's the atoms that are attached, and it takes into consideration the shape is altered by the lone pair. Make sense?
Yep.
Yep.
Okay. Okay, let me clear this. Okay. So what about these guys? H2O, SF4, and Zion fluoride 4. I mean, Zion tetrafluoride. Was that structures?
Hmm.
Kayla,
Yeah.
talk about water. Lewis dot structure.
It'd be, well, hold on, I have to write it down.
Would it have to be like the O on top?
Okay.
And then since there's two H's,
Okay. And lone pairs?
Yes.
yes.
How many?
2 sets.
Or
2 sets.
sets.
Okay. So what would be the wedge dash model? Or would there be a wedge dash model?
Or wouldn't?
Okay. Okay. And what is the EPG? Electron pair geometry?
Linear.
Would this one be the bent?
Okay. The EPG,
Oh, no.
electron pair geometry.
Linear?
Are you sure?
I want to say yeah.
How many attachments does it have? How many attachments does the oxygen have?
2.
Including,
Two.
and no, including the lone pair.
4.
Okay, so if it's 4 attachments, then what is going to be the EPG?
Tetrahedral.
That is correct. Tetrahedral.
I said it so slowly.
Okay. Yeah. Well, that's because you have 1, 2. That's technically it's kind of like having 4 things attached to it. 1, 2, 3, 4. Right. So the EPG is going to be tetrahedral. But what did I say about the lone pairs? What do they do?
They're going to alter the shape.
Okay, so they're going to alter the molecular geometry. So what is the molecular geometry then?
Bent?
That's right, bent.
So
Good
could I
job.
remember bent like when I see model with like 2, this is the way I'm trying to imagine it. Like the O has 2 little hands and it's pushing down the H's. Like
That's
go
it.
away.
Yeah, that's exactly what's happening in a sense, right? Because
Yeah.
those lone pairs are doing that. They're just kind of pushing them together, right?
Mhm.
You know? And yeah, and it's on the oxygen. So yeah, that is a good way of imagining. Good job. I have to use that analogy. Okay, so what about the sulfur? I mean the sulfur tetrachloride.
Sulfur's in the center. 4 fluorides around it.
Okay.
But sulfur's the exception.
How many lone pairs does sulfur have?
1 set. 2, 4, 6, 8. Right?
Okay. So the electron pair geometry. So I'm not so sorry. Yeah, let's do the EPG and then we'll do the wedge dash model.
So is this okay? And don't yell at me because I'm having a hard time reading it. Trigeminal pyramidal,
Trigonal,
trigonal. My bad. It looks.
trigonal, bipyramidal.
Sure. It looks like bi.
Okay.
It's fifth row, first column.
Okay. So there's 5 attachments, right? So
Because you count the lone pair.
that's right. So it would be trigonal, bipyramidal.
Bipyramidal. My bad.
And then the molecular.
So because there's one lone pair, so we'd have one single wedge, one dash wedge. So this would be the seesaw.
Okay. So then you said we'd have, so it'll look something like this, right? Okay, so then we'd have one coming out. One going back. And one to the left. So we'd have S, F, F, oops. Should be like this. Okay. Okay, and then the last one. Spin around.
Xenon.
Okay. And then how many attachments and how many lone pairs?
Four attachments.
Okay.
And
Could noble gases hold more?
Yep, if they're beyond the 3rd period. Is he not beyond the 3rd period?
Yes.
Okay.
So they're able to.
would it have 2 sets of lone
Okay.
pairs?
2 sets. Yep, so that'll be a total of 8 valence electrons, which all noble gas have 8 valence electrons. That's what makes it noble. So the structure is going to be what? Or what is the EPG?
Octa.
Okay. Octahedral. And then the MPG.
Squared.
Square what?
Planar.
Okay. So then is the structure is going to look like this. Simplest way to draw it would be one plane. That's being lazy. Let me put my electron pair geometry. And you'll notice the wedge dash, we don't add the lone pair. Okay. Simple.
Did you just not do the wedges?
Well, there's no wedge because it's all in one plane. So you don't have to. The only time that you have to draw wedges is if you're really having a three-dimensional structure, right? Or if you're just trying to make it so it's three-dimensional, right? So if you did the wedge dash the other way, you would have two that would be coming out towards you, and then ones that'll be going down in the back of you. But they could all be in the same plane, so then they're just stick structures.
Okay, I was just wondering because on the slide it shows it on here, so that's why I was just wondering.
Yeah, it's actually would be incorrect on that slide. I just so yeah. Okay, so this is just showing you those images. Okay, questions, concerns, Cash. Now, occasionally we'll have to do things that are a little more complicated, right? Let's say we have, this basically is an amino acid.
Looks like a hot mess.
Yeah, and the way that it's written, it tells us how to write it, right? So we know that here we have this nitrogen.
NH2, okay.
And it has two hydrogens. It's attached to this carbon. And then that means there's going to be a lone pair there to make it complete. And this carbon has three hydrogens. Technically, it should be two hydrogens. Oh, wait a minute. Sorry. Let me correct that. We have this nitrogen attached to this carbon, and this carbon is also attached to this carbon. So you have this.
Dr. Henry.
Yep.
Quick question. Why wouldn't it like the NH2 be attached to CH3 and then continue on to CHCOOH?
Because it will make it terminal, right? Because if there's three carbons here, that means that it would have a carbon here, and a carbon here. I mean, sorry, a hydrogen here, and a hydrogen here. So it wouldn't be, that's not feasible, right? Because the carbon only is going to have at most 4 attachments. It's never going to have 5 attachments or 6 attachments. For it to be able to continue to attach, it would have to have another attachment. So that suggests that both of these guys here, both of these structures here are attached to this carbon. So then in actuality, you'll have, let's see, dot, dot. We have this carbon. It has 1 hydrogen attached right here. Then it's attached to another carbon that is terminal. That's why it would have 3 hydrogens.
So terminal is just another form for complete.
Yeah, or end.
Okay.
Like
Okay.
a cap, yeah. And then it's attached to another carbon, right?
Okay.
And then this here is going to be, one of them is going to be a double bond. And then the other one is going to be a single bond with a hydrogen coming off of it. Okay, so anytime that you see this, it's always going to be this structure here. Okay.
Okay.
Does that help?
Yeah, that makes more sense.
Okay, so, and this
But
is
it's
a
a hot mess.
pretty picture of it, other than my pick and scratch. Okay, and so the wedge dash is going to be very similar. This guy's going to be coming out. That one's going to be going back. That one's going to be in plane. This one is going to be coming out. This one's going to be going back. Okay, and then these guys are planar, so they don't have to be three-dimensional, right? So this guy is, what would be the structure just around this end if we just looked at the end? What would be the electron pair geometry and the molecular geometry? The EPG is what?
Would that be tetrahedral?
EPG would be tetrahedral, that's correct.
So then the molecular would be trigonal pyramid.
That's right. And then this guy would be, let's see, so tetrahedral. And then you said Trigonal Pyramidal. Okay, what about this carbon here? EPG,
Tetrahedral again.
right?
Well, actually be both, right?
They both would be tetrahedral, that's right. And MPG. MG. Okay, and what about this carbon here?
Do you count that as 4 or 3? Because it's double bonded.
The double bond only counts as a single attachment.
So it's 3.
Yeah. Yeah.
So trigonal planar.
That's right. So EPG, trigonal planar. And then what about MPG?
The same.
Okay. And the oxygen?
2, 3, 4. Tetrahedral.
Okay.
And bent.
That's right. Piece of cake?
Now.
Okay, so the last thing that we're going to be talking about is polarity. Okay, so bond polarity is just the polarity between two bonds. So we know that in the case of, although this is, there's a small difference in bond polarity between carbon and hydrogen, but we know that it doesn't make enough of a difference to cause the electronegativity to be an issue. So it's not really favored. So they're about even, right? In the case of the carbon and the hydrogen. So almost even though there's going to be a very slight pull towards carbon, but it's not going to be much of a difference, so that it really shifts where the electron is going. Where we have beryllium and fluoride, there is a huge difference between beryllium and fluoride in terms of electronegativity. So the electrons are going to be going in this direction, right? It's going to spend more time with the fluoride than it's going to be spending, not with beryllium, with boron.
Boron.
Yeah, with boron. Okay. So in this case, the bond polarity between two atoms is measured by that electronegativity, right? And we know that fluoride is more electronegative than boron. So then the electron is going to be spending more time here. So then we would shift it in that direction for that particular bond. Okay. And when we're talking about molecular, we're talking about the full thing. We're not just talking about a single bond. Okay. We're talking about the whole molecule. So when we're talking about molecular polarity, we have to look at the entire thing altogether. Okay, rather than just between two atoms. Does that make sense?
Yeah.
Okay. So here's an example. We have carbon dioxide. Well, they're both being pulled towards the oxygen in both situations, right? The electrons being pulled towards the oxygen. So they're both being pulled evenly towards the oxygens. So neither of them are going to be favored, right? So the overall dipole moment is going to be 0 because you're having pull going in opposite directions, and neither of them are pulling more than the other because they're both oxygens, right? So overall, it's kind of like you're having twins that are exactly the same strength, that are exactly the same height, that are pulling on you on both sides. If you're in a moving chair, you're not going to be pulled one way or the other. Make sense?
So she's equalizing.
Yeah. And so
Okay.
they balance each other out, so you're going to have an overall of 0 dipole moment. Where oxygen, in the case of water, we have the electrons being pulled towards the oxygen, right? Both sets. So both of them are going in the same direction. So this is going to be kind of like an additive effect. So they're both going to be going towards that oxygen. And so your overall dipole moment is also going to be going towards that oxygen. So overall, we're moving towards the oxygen because oxygen is pulling both of them towards it. Does that make sense?
Yeah.
Okay. So water is polar and carbon dioxide is nonpolar. Okay. Good, bad, or ugly?
Good.
Okay. Questions, concerns, Cash? Okay. So if we do polarity for, let's say, we'll do bond polarity for CSO, and then we'll do bond polarity for CH3Cl. Okay. For CHO, so let's draw the Lewis dot structure for this guy. Who's going to be in the center?
Carbon?
Okay. And then we have oxygen on one side.
Or there's 6 for oxygen. And 6 for sulfur.
Okay. So Lewis dot structure for both there. Okay, so in terms of bond polarity, who's going to be favored?
Oxygen.
Oxygen. Okay. For
But-
carbon and okay. And what about carbon and sulfur?
It would be the sulfur again, right? Because
Okay. Okay. So overall, who's going to be favored?
oxygen.
Oxygen. So if we add them up together, the overall thing would be oxygen. Okay. Because oxygen has a stronger pull than sulfur. So it's kind of like saying cousins that are pulling you on both sides, but one is much stronger than the other. Okay. So
Because it's electronegativity goes from left to right and then bottom to top, right?
what do you mean by for left to right?
For on the
yeah.
on the
Oh, yeah.
so it goes across and then it builds up.
That's right. Yep,
Okay.
that is correct. Okay. Questions, concerns, Cash?
Dr. Henry, how would like on this one, how did we know that oxygen would be like the most popular one?
How do we know that oxygen would be like the most popular one?
Yeah. Like, how do we know
Because-
that it was going to have a stronger pull than sulfur?
Because we know that it has a stronger electronegativity, right? So we've talked about electronegativity last time.
Yeah.
Yeah. So,
So that's what I was saying, Abby, when you go look at your periodic table,
Yeah.
going from left to right and then top to bottom. So helium and all those in this corner are going to be more electronegative.
Oh, okay. Okay.
Remember? And I think there's Dr. Henry, I think you gave us a paper too that showed us that.
that's right.
I'll
Can you
try
go
to
for-
find it. I'll find it, Abby, and then I'll text you a picture of it.
Oh, thank you. Because I was about to say that. I'm like, oh darn it, I need to go find the other paper.
And
I gotta look through the chemistry Bible. It's not a
Yeah.
binder, it's a Bible.
okay. And so I want you guys to think about this last one, the very, very last one, and then we'll finish it up next on Wednesday.
Yep.
Okay. So there's going to be a lab that is going to be posted for you guys to do, and it's going to be dealing with kind of a little bit with polarity. It's going to do with intermolecular forces. Okay. And I'll
a
be
sim
posting
one?
it later today. So don't worry about it till Wednesday. Okay. And your test is actually going to go live tomorrow morning. Okay. And you'll have until Monday of next week to get it done.
Is
'Cause I
that
was behind on
polarity?
everything. What was that?
Sorry, is that polarity? Is that a simulation lab?
No, it's going to be a real lab. We're
Oh, okay.
making slime
Oh, okay.
Ooh, on Wednesday?
on Wednesday. Yes.
Yes.
Okay?
Oh, Dr. Henry.
Yes.
I saw your the comment that you left on my lab too.
Yes.
I resubmitted it and then I noticed that the table was getting cut up again. So I submitted an attached file in the comments again, like twice.
Okay.
You're probably gonna see my comments. You're gonna be like, she was freaking out. Like,
Okay. Which I always think about you anyway, so it won't be any different. It's okay.
I was freaking out. You can see my comments. They're like, oh God, this girl's a mess.
Yeah, and I actually had that comment with a lot of your guys's. So you guys go ahead and make the corrections, and really, what I want you guys to do, because literally one of the exam questions are exactly the same thing that you guys are doing for that lab. Yeah.
Oh, okay. Can I show
For-
you my table and you can tell me
For which
if
one?
here? Let me show.
For the spectroscopy lab, the modified question. So what you guys, the calculations that you guys did for that table is exactly, it's going to be exactly what you guys have for one of your problems. So frequency,
Yeah.
energy, and then number of photons, right?
Dr. Henry, could I show you my table and then you can tell me if this is correct?
I actually can't because I'm already late for my other class. That's
Oh, okay. I'll
but
just show you on.
yeah, if you catch me up later, like later on today, then
Yeah.
we'll be able to do it then. Okay.
Okay.
I'll talk to you later.
All right, bye.
Bye-bye.
All right. See you on Wednesday, Dr. Henry.
I'll see you guys on Wednesday. Sorry to rush out.